Okay, so what we want to look at today, guys, is how do we read graphs? I mean, we're going to look at a couple of types of graphs in particular, but we're going to look at how do we read graphs or interpret graphs in general. All right, because all graphs essentially work the same. It's what's on them that's different. All right, so basically the slope of any graph tells you the relationship between, the numerical relationship between your manipulated variable and your responding variable. How much does my responding variable increase or decrease as I manipulate the manipulated variable? All right, things like that. So the slope always tells us that relationship. Okay, the two graphs that we're going to go over today, okay, position versus time and velocity versus time graphs, have a particular thing that their slope represents. Okay, and do we need to know what that is? Yes, we do. Do we need to memorize what it is? No, we don't. Okay, that's kind of what I'm going to show you here. A lot of people will try and memorize what's, oh, the slope of this kind of graph represents this, and the slope of this kind of graph represents that, and that might get you through Science 10. If you're really good at memorizing, it might get you through Physics 20, where we have about, 20 different graphs that we got to use. Get to Physics 30, Chem 30, Bio 30, and Physics 30, there's probably about 40 graphs. Chem 30, 15, 20. Bio 30, about a dozen. Pretty hard to memorize. We're looking at like 50 graphs, like more than 50 graphs there. Okay, that we would have to memorize what the slope represents and what all the, it's just crazy. Okay, it's way easier to just look at a graph and say, here's what's on the graph, and logically kind of deduce how you might get something as opposed to memorizing how you would get it. Everyone kind of follow me there? Okay, so I'm going to show you kind of how you can do that. So we got to understand what kind of information can be read from the two types of graphs, position versus time, velocity versus time. Okay, we're going to look at how the equations that we're going to use in this class come from graphing. We already looked at how the v equals d over t1 is actually the slope of the line on position versus time graph already. And we're going to look at, well, I guess that's the same thing here. They show it in the same way and how they're derived from each other. Okay, questions so far? All right, so on a position versus time graph, we see where an object is at various points in time. Right? It basically tells us or plots a map of a trip, is basically what a position versus time graph does. Okay? So in looking at that, we know where the object was, and from that we can also figure out how fast it must have been moving in order to get there. Right? Because if it went really, really far in a short space of time, it was obviously going fast. But if it didn't go very far and it took a really long time for it to do it, it was going really slow. Okay? Those are the things that we can just know by looking at a position versus time graph. We can just interpret those by the shape of the graph, okay, and where the points are. Okay? There's other things that we can calculate, but one of the skills we've got to have is to be able to look at a graph and say, what's going on here? Okay? I once put this exact graph, this one on the left, okay? I actually put this graph on a final exam once. Okay? And all I asked was, I put like A, B, C, and D. And the question was, describe what is happening to the object in each of the lettered sections. Okay? So this is a graph that's showing the position of the object as a function of time. What is the object doing in part A? Nothing. Yeah. Because its position didn't change. It stayed in the same place, right? It's a flat line. At time 0, its position was 20 meters. And at time 1 second, its position was 20 meters. Didn't go anywhere. So it didn't do anything. So this is a stationary object. Okay? A flat line would indicate that it's not moving, right? And we said the other day that the slope of this line would be the speed of the object. Agreed? Well, if the slope is 0, the speed of the object is 0, the object's not moving. Okay? So it all kind of logically goes together. All right. What is it doing in part B? Okay, moving how? Moving forward. Okay, I like that. Moving forward, constant speed, accelerating. we want to say accelerating. Everyone wants to say that when we first start this because they see a line that's going up. But it's actually a constant velocity because this isn't the speed that's going up, it's the distance that's going up. How far? But is it going up at the same rate? Yes, it is. So that's actually showing a constant velocity. Every second, it went another 20 meters further. So that's showing an object moving forwards at a constant velocity. All right? And that would be what I would have been looking for as an answer on that exam. Those two things, moving forwards at a constant velocity. Okay? Everyone follow me there? Okay? It's not that moving at a constant speed would not have also been correct. It's just that moving forwards at a constant velocity would have been more correct, okay, more accurate in that case. Okay, what's going on in part C? Same thing as part A. The position stayed at 60 meters the entire time, which means the object did not move. Right? There was no slope to this line, so there's no velocity. What's it doing in part D? It's moving backwards at a constant velocity, right? Because now we went from position 60 down to position 20. We went backwards. Okay? And we did so at a constant rate. Everyone follow me there? All right? So really what this object did is it stood still for a second, and then it went forward 20 meters, or sorry, it went forward 40 meters, and then it came backward 40 meters. Okay? Everyone all right with that? Okay. Now, other things that we're going to be asked to do, okay, would be, and actually I think I used this graph twice, the same graph twice on the test actually. So in one question I just asked, what's the object doing? Just describe the motion. And then in another question I asked them, what's the total displacement of the object in this graph? It's 0, yeah, okay. I mean, really, and I think I made that like a 1-mark question. It wasn't, there was no marks for work because I expected that people would look at that and go, it started at 20, it ended at 20, didn't go anywhere, okay? That it didn't require any work to solve that, okay? My initial position was 20 meters, my final position was 20 meters, I went forward and backward and came back to where I started from. Everybody okay with that one? So what's the average velocity over the whole trip then? Also 0. Okay, remember, average velocity is total displacement over total time. And the total displacement was 0. So average velocity is 0 then. Okay, so, and sadly, people did not do well on this question. Okay, sadly, because really, there wasn't any really difficult math to do here, was there? It was a matter of, can you understand what the graph is telling you? All right, another thing I asked them was, how far did the object go? So I've already asked you for displacement, so asking how far the object went is asking for distance. Okay, does distance care whether you went forward or backward? Nope. All right, so what I have to do to find how far it went is basically look at all parts of the graph separately and then add them all up. Okay, well, this part's easy. 0. All right. Then I went from 20 meters to 60 meters, which is, then I went 0. Okay, and then I went from 60 back down to 20. How far did I go? 80 meters. Okay, again, not a difficult calculation. All right. Then I asked them what's the average speed over the whole trip. How do I do that? Please? 80 divided by 6. Total distance over total time. Okay, so we go back and forth between our formulas and the data on a graph a lot of the time. Okay, but again, it's not making really difficult calculations, but it's making you understand, or at least show that you can interpret what's going on the graph. Okay, all right, so far so good. Here's another position versus time graph. It's a curve. What is that object doing? It's accelerating. Okay, it's going faster and faster and faster. How do we know that? Okay, we could memorize that it's a curve and a curve means it's accelerating. Okay, but if I look at where the points are. In the first second, it hardly traveled anywhere at all. Went like a meter maybe. Okay, but the next second it went from 1 meter to 10 meters, or actually probably 9 meters. So did it travel farther the second than it did the first? All right, then it has to be going faster. Okay, and same thing here. It went from 9 to 19. So yeah, it's going faster. It's going faster and faster because it's going further and further. You can see the distance between these lines gets greater every second. Okay, that's because it's going faster and faster. So if you travel farther each second than you did the second before, it's because you're going faster. Okay? And that gives you a curve. All right, making sense so far? Yeah? And what if it wasn't a position versus time graph? Okay, what if it was, let's say, would you be happy with that graph? If it was your money, you would. Yes, but it's exponential. If you continue to wait, that 50 will become 750. Yeah. Okay. Yeah. Well, still, I think you'd be happy with exponential growth of your money. Yeah. Okay. Yeah, after a year, yeah, absolutely. Okay. Exponential growth of your money after a year. I mean, what did you put in? $1. Well, I mean, that's not too bad then. Okay. If you started with $1, well, then you're not doing too bad. Okay. So exponential growth just means that it's growing faster and faster each time interval than it was the interval before. Okay. All right. So things we can read right off of a position versus time graph. We can read where the object is and when. Okay. That's really all you can read off of there. Okay. But we can calculate total distance, total displacement, average velocity, and average speed. Okay, we can calculate all of those things off of that graph. Okay, we can't read them directly, but we can calculate them. All right, does everyone follow the difference on that? Okay, because really, if I'm just looking at the graph, the only thing the graph outright tells me is the object was at position 60 meters at time 3 seconds. That's really all it tells me. Okay, but from that information, I can find other things. All right. So little things in here, okay, if the graph is a curve, the object's undergoing acceleration, okay, either positive or negative. Okay, if the graph is a line that's parallel, the object's position's not changing, so it's standing still, okay. Okay, little things like that. All right, now we've gone over slope calculations already. Okay, you can do that with rise over run, but we were saying that we preferred to use this one, okay, simply because it will allow us, which you have to do in your lab, of course, to extrapolate for values that are beyond the graph. Okay, now how do I get slope from that formula again? Which part of that formula represents slope? M. Okay, so if I want to solve for slope, what do I do with B? Subtract it. So I got y minus b divided by x. Okay, which we said is basically the change in y over the change in x. Okay, that's really all we're saying, right? Because if we continue that line down, that would be b, right? So we could say that this is y, that's b, so y minus b is the height of my triangle, okay? And x minus 0 is the change in x, right? So that's what we're doing with that one. Okay, looking at this graph here. In part A, what's the object doing? Moving forward at a constant rate. Okay, it's moving forward at a constant velocity in part A, right? And it goes how far? 6 meters. Okay. It goes 6 meters forward or in a positive direction. We would assume positive would be forward here. Okay. What's going on in part B? Staying still, right? Because its position at the beginning of B is 6 meters. Its position at the end of B is 6 meters. It hasn't gone anywhere during that 4 seconds. Okay. All right. Part C, what are we doing? We're reversing at a constant rate. Okay, so we're traveling backwards at a constant velocity. How far do we go? Negative 16 meters, yeah, okay, because we go from positive 6 to negative 10, okay, so we went backwards 16 meters in that case. Okay, part D, staying still. Where am I going faster, E or F? Are you sure? E. E is steeper, okay, and steepness is slope. What does the slope represent on this graph? Yeah, velocity or speed. Yeah. Okay. So if I calculate the slope of E, it's definitely going to be greater than the slope of F because it's a steeper line. Right. So the steeper the line, the faster you're going. Okay. Everybody all right with that? Okay. Now I want you to calculate something for me. What's the total displacement of this object over the whole trip? Yeah. No, you're right. It's 0. That was a quick one. Okay, 0, because it started at 0 and ended at 0. Remember, guys, there's a quick way to calculate displacement. Okay, final position minus initial position. If they're the same number, it's 0. Okay, that's the kind of quickest way to calculate total displacement. All right, what's the total distance traveled? Okay, what did we have to do the last time I asked that? Right, we got to add all the parts together, which we did in all those multiple step problems that we did as well, didn't we? We had to find the distance for every section and then add them up. Well, that's what I got to do here. How far did I go in part A? 6. How far did I go in part B? Part C was 16. That's negative 16, but I mean, we won't worry about the negative when we get to that part. Okay. D, 0. Okay. And for E, we went from negative 10 to 4, so that would be 6, and here we went 4. All right, so there's 10, 26, 32. Right? All right with that. Okay. So sometimes it looks daunting when you first look at a graph. Like this graph's got all these sections, and it looks like, oh man, it's going to take me forever. But really, it doesn't. Okay. Break it down piece by piece, and you can have a question done in no time. All right. What about the average speed? Not 0. The average velocity would be 0 because the displacement's 0. Yeah, 32 divided by, we'll say that goes to the 18. It's maybe like 17, but we'll say it's 18. Okay, so if I go 32, the total distance traveled, divided by 18 seconds, right, it's going to be like, what, 1.8 or something like that? We'll say something like that. 1.8 meters per second. This will be somewhere in there. Okay. Total distance over total time. Okay? So just because we're working with a graph doesn't change how we solve problems. Okay? We could have had one of those multi-step or multi-part word problems, and this would have been the graph for it. Okay? They all kind of look the same, right, when we get to this point. Questions so far? Is that making sense? All right. Here's where it gets wonky. Not so much, it's not really difficult, but it's wonky. Okay. The object that's on this position versus time graph is doing a lot of what? There's a lot of accelerating and decelerating. It's changing its speed a lot. Okay, so we got all these curves. Once in a while, a question will ask you, what's the instantaneous velocity at this point? Okay, so in other words, how fast was it going at exactly this time or exactly this position? Okay, well, normally we calculate speed or velocity by going total displacement over total time, but that's not going to tell me how fast it was going here because the speed is always increasing. It would maybe tell me the average between these 2 points, but that's probably not going to be the speed right here. All right. Similarly, I can't just go d over t for that spot because that's going to be the average between here and there. So again, that's not telling me the instantaneous velocity. Now, when we had our graphing lab, we had all these lines on position versus time graphs, and we calculated their slopes, and the slopes represented their speed, okay? Because it was essentially the total distance over the total time. Everyone follow me there? Okay. I'm going to teach you the only thing I understood in university calculus. It was the longest 5 months of my entire life because I understood only this thing, and it was on the first day. After that, I was totally lost. I still passed the course by memorizing all the examples in the textbook and writing them down on my final exam and getting part marks for method. I kid you not. That's how I passed calculus. I don't recommend that as a way to pass calculus, but I was desperate. I had no prayer other than that. Okay, so this just goes to show just how bad I am at math. To a mathematician, a curve is an infinitely large number of infinitely small straight lines strung together. Right? It would be like if you were watching like a really low resolution video on YouTube. What do you see? You see the pixels. You see the little squares. Okay? Because that's how a computer makes curves. Okay? Computers are on or off, zeros or ones. Okay? So a pixel is either on or off, and then there's different ones for color. But okay, it's either on or off. Now, the smaller the pixels, the smoother the picture is. The bigger the pixels, the worse it is. Everyone follow me there? So if you're watching like something in 1080p, it's 1080 pixels by 700 and something pixels. Anyway, it's got lots of really, really small pixels. So small that we can't see them. We can't see the individual squares. So the picture looks really clear. All right? That's what a curve is. A curve is an HD picture of all these little tiny lines. What we want to do is zoom in on the little tiny straight line that exists right here at point A. Because if it's a line, we can calculate its slope. Except that how are you going to get like y and b and all of that kind of stuff for a line that's this big? The answer is make it longer. Okay? How many people have heard of what a tangent is? Okay? A tangent is a line that touches a curve but doesn't cross it at a certain point. Okay? If it just touches the curve there, it's parallel to the curve at that point. So if it's parallel, does it have the same slope? Yes, it does. So what we want to do is we want to draw a tangent that touches the curve so that we can make it nice and long and find the slope of the curve at exactly that instant in time they were asking us about. All right, so here's how we do that. You take a ruler, okay, or I cheat because I have to use the straight line tool. Okay, and I draw a line that touches the curve at that point but doesn't cross it. I don't know if I really like how that ended up. But here's the beauty of my line. I can adjust it later. I like that a little bit better. Okay, so now I've got this nice long line, okay, that I can use and I can calculate its slope. Okay, because now it's long enough that I can hopefully get a grid intersection, maybe a y-intercept, okay, and go from there. Everyone follow me on that one? Okay, so if I want to calculate the slope of this line here, okay, I've got a grid intersection right there that I can use, okay, and I've got one right down here that I can use as well. I don't have a y-intercept, so I'm going to have to go the old-fashioned way and go rise over run. Everyone okay with that? Okay, in this case, that's fine. Okay, I can do that. All right, so if I want to find the instantaneous velocity at point A, I'm just going to find the slope of my line there. So I'm going to go y2 minus y1 over x2 minus x1, okay, because I don't know what b is. It's below the line here. Okay, so that's going to be 6 minus 2 over 12 minus 6. All right, so I've got 4 over 6. Okay, so 2/3, right? So 0.666, okay, is my speed on that one, meters per second, is my instantaneous velocity at that point. Okay, everyone all right with how we did that? All right, what's the instantaneous velocity at point B? 0, yeah. Okay, I mean, if we follow the same logic that we just did and we draw a line that is tangent to the curve at B, it's going to be horizontal. Okay, well, it's not touching it, but I'll make it touch it. Right? That touches the curve at B, but it has no slope, does it? It's just 0. Okay? Because what this object is doing in this part here is it's turning around and going the other way. Right? This would be a graph, at least this part of the graph would be a graph of this. Okay? As soon as it leaves my hand, what's gravity doing to it? Pulling it down. So it's accelerating downwards as soon as it leaves my hand. So it slows down, it slows down, it slows down, stops instantaneously, and then starts to speed up in a downwards direction. Okay? So this is slowing down here, and then this would be speeding up. Okay? So as the line gets flatter, we're seeing an acceleration that is negative. That is, it's slowing down. Okay? If it's going steeper, then it's an acceleration that is speeding up. Okay? I have never asked someone to do that on a test. Okay? For a couple of reasons. First off, everyone's going to draw that tangent differently, and I'm going to get an incredibly wide range of answers. Okay? And secondly, I can ask you if you can calculate slope in much better ways, but it's still important for you to know how that works. Okay? Because there could be worksheets and things like that that would ask you to do it. Okay, everyone clear on that so far? Yes? Okay. All right, next one we're going to look at are velocity versus time graphs. So now, they're not showing where the object is, they're showing how fast it's going. Yeah, now we can see how fast is the object going at various points in time. Okay, this is a position versus time graph right here. Okay, and this is a velocity versus time graph right here. What do they have in common? They're both showing an object traveling at a constant speed. Okay, on a position versus time graph, that shows that the position is changing or increasing every second. Okay, everyone with me there? All right, that's what this one is showing. It's showing it going up at a constant rate. And this is showing the velocity not changing. So it's showing an object traveling at a constant velocity. Okay? But it looks weird. Okay? I don't know how many times I've put a question like this on a test and asked people and put it like with velocity in meters per second, the whole works, a complete graph on as a multiple choice question and said, what is the object doing A, B, C, or D? And I had one of them be nothing. And you would be surprised how often people pick nothing when they look at that graph. Okay? Because they just see a horizontal line. And they just go right away to, well, nothing's changing, so nothing is happening. But that's not true. Okay? This is showing something that is moving. It's moving at a constant velocity. It's just that that velocity is not changing. Okay? So there's not nothing going on here. There's an object traveling at a constant rate. Everyone okay with that? This graph and this graph are of the same exact object. Okay? How could I find the velocity of the object from the position versus time graph? What's that? Yeah, I could use y equals mx plus b and calculate the slope of the line. Okay, let's do that. Okay, my y-intercept is actually what here? It's 100. Okay, so y equals mx plus b. Okay, I'm going to use this spot up here to get my y and x values from. Is everyone okay with that? I mean, I could use any of those points, but I'm going to use the last one. All right, so I'm going to manipulate for m. So m is going to be y, which is going to be 1400, minus b, which was 100, over x, which was 5. All right, so we got 1300 over 5, which is what, 260? All right, 260. I've used that graph a few times. I didn't do that in my head. Okay, 260 meters per second is my average velocity for this graph. Is that about where this graph is saying it is? Yeah, because this line here would be 250, right? So that's just above it. Right, we're showing the same thing. All right, what if I move this line back down here? Now what's that graph showing? That's showing an accelerating object, right? Because now the velocity of the object is increasing. It's going up. Okay. All right. Now what's it showing? Yeah, is the object still accelerating? Technically, yes. Acceleration means a change in velocity over time. Is the velocity changing over time there? Yeah. Acceleration in physics means just a change. Doesn't have to be positive or negative. In fact, we rarely use the word decelerate in physics. Okay? That's a negative acceleration, right? Or a positive acceleration. But we don't use the word decelerate. All right, so this is showing still a change in the velocity. Everyone all right with that? Okay. So I just told you that acceleration is the change in velocity over time, right? So the velocity of the object's changing over time. So what would the slope of that line represent then? Acceleration, exactly. Because if I found out the change in y, that would be the change in velocity. And if I found the change in x, that would be the change in time. Okay, now you don't know anything about acceleration because I haven't taught it to you yet, but you just figured that out from that graph. Okay, that's the skill you got to be able to have when you're analyzing graphs, is to be able to look at any graph you're given and go, here's the two things that are on it, and if I found the slope of the line on this graph, it would represent this. Okay, you don't have to memorize it, you just have to look at it. Okay, look at it and go, okay, change in velocity divided by time. Okay, well, maybe you don't even know that that's what acceleration is, but you could say that the slope of this line would represent the rate at which the velocity changes over time. Okay, without even knowing that that's acceleration, you could say that to somebody and be right. Okay, everyone follow me on that one? Okay, so if I had, let's say, a graph that looked like this instead, okay, the slope of that line would tell me what? Yeah, the rate at which I decrease my energy. Yeah. Okay, I'm decreasing how much energy I use every hour by a certain amount. The slope of the line would tell me that. Okay, I have no idea what that's called. Okay, it may not even have a term, but I was able to figure it out just by looking at what's on the graph. It doesn't even matter whether you can really, use a proper term for what the slope represents, as long as you can say or describe what the slope represents. Okay, that's the important skill we've got to be able to have. Okay, let's go back to this graph here before I wrecked it. Okay, what if a question gave me that graph and then asked me to calculate the displacement of the object? Exactly. Go 260 times 5. Okay, I'm looking at that graph and I'm saying, okay, I know what the average velocity is because it doesn't change. It's 260. and I know how long it travels at 260 meters per second for. Okay? So really, all you did was this. Right? We're going to find the total displacement by using the average velocity, which we know, and the total time, 5 seconds. We just manipulate it, v times t equals d. Okay? Everybody all right with that? It's easy when you're looking at that and it's going, all right, it's not changing. Can you still do it? Okay. When you calculated the displacement of this object here, you basically went base of the rectangle by the height of the rectangle, yeah? So could you do the same thing even though now it's not a rectangle? Sure you could. Okay, this thing is still, it's changing its velocity, yes, okay, from down here to up here. It's changing its velocity, but it's changing it at a constant rate. So it went from 100 to 500, okay, over the course of 5 seconds. So its average velocity is where? Right smack in the middle, right? Half of the trip it was going faster than this number, and half the trip it was going slower than that number. So the average would be somewhere in the middle. How do you calculate the area of a triangle? Base times height divided by 2. Well, is the height of this triangle divided by 2 that point we were just talking about? It is. And then if I multiply that by the base, I'm just going average velocity times time. Exactly what we said we would do, okay, for this. Right? So it's a matter of, I gotta look at what's on the graph and see if I got a formula that I can use that applies to that graph. Okay? A little bit tricky. That's probably the trickiest thing you'd ever be asked to do using a graph. Okay, would be to do that calculation there. Follow me so far? That's usually the part that really throws people. Okay. You guys, your eyes aren't glazed over, but some of you look unsure. Do I need to explain that again? Yes? No? Okay. Okay, what's going on in that graph? It's a velocity versus time graph, keep in mind. Right, the object or the person in this case is accelerating, and then they're staying at a constant speed for a little while, and then they are, or slowing down, right? They're accelerating negatively. In fact, they don't just accelerate negatively, they actually come to a stop because their velocity actually reaches 0. Okay, so this is what a graph of a sprint looks like. Right? You come out of the blocks and you're accelerating, then you just reach a point where it doesn't matter how hard you push, you can't run any faster. Okay, you run at your maximum speed for a little while, and then you cross the finish line and you come to a stop. Okay, now depending on what kind of a runner you are, the length of this line shifts and the length of this line shifts, okay? And depending on whether you're a slow accelerator and all about top speed or whether you're a quick accelerator with a low top speed, okay? In the end, you want to reach the finish line before everybody else in time, right? Okay? It's a weird thing, but you don't have to be the fastest person out of the blocks to win a race, okay? I don't know if any of you guys have ever watched this, but in '96 when Donovan Bailey won the gold medal at the Olympics, he actually tripped coming out of the blocks. Usain Bolt did it once too and still won a gold medal. Tripped coming out of the blocks, but they just had such incredible top speed that they reeled everybody in by the end. Okay, everyone got ahead of them early, okay, but they were able, their graph was up here. Okay, their top speed got them to the finish line quicker than everybody else. And that would be Usain Bolt, because that would be less than 10 seconds. Same with Donovan Bailey, less than 10 seconds. Okay, very, very quick. Right? People who accelerate very quickly but have a low top speed would be a steeper line on this graph. Okay, so I probably didn't draw that right. Okay. Okay, and then it would be something like that, right? For a person with a high top speed but a slow acceleration, a person with a great acceleration and a lower top speed would be the lower line. Okay, something like that. It's a weird thing, but yeah, that's how it works. Okay, now, what was I doing with that? Oh, units. That's what I was explaining with that. Okay, let's do that again. All right. For a velocity versus time graph. So we got meters per second and seconds. Okay, so I got a velocity versus time graph here. Okay, and I've got this object that is doing what? They're changing their velocity. They're accelerating which way? Positively, right? They're going faster in a positive direction. Okay, if I find the slope of this line, okay, we said that that represents acceleration because it's the rate at which I change speed over time. Okay, what do you suppose the units for acceleration are? I mean, the units for speed are meters per second. The units for velocity are meters per second. What would the units for acceleration be if it's how fast I change my meters per second? Well, but that's actually speed, 1 meter every second, right? That's a speed. So 1 meter per second faster every second. Okay, so 1 meter per second every second is meters per second. Okay, yeah, yeah. It's just the way you were saying. You just kept you kept forgetting the second part. Yeah. Okay. So acceleration is in meters per second, which we look at in terms of fractions here. If I'm dividing fractions, it looks like that, right? Meters per second divided by seconds. When you divide fractions, what do you do? Right. You take the reciprocal and then you multiply. Okay. So instead of dividing by seconds over 1, I'm multiplying by 1 over seconds. Meters times 1 is meters. Seconds times seconds is second squared. Meters per second squared is how we say it. It's meters per second, but we say it as meters per second squared because that's mathematically what it would come to. Okay. All right, here's how we get that. If I'm finding, let's say, the slope of this line, I'm going to use those points there, and then that's 8, I think, so, well, that's perfect. All right, so I'm going to find the slope of this line. I'm going to use y equals mx plus b. Okay, and I'm going to solve for m. So m is going to be y minus b over x. So that's going to be 8 minus 2 over 8. So we'll have 6 over 8. So that's 3/4, so 0.75. Okay, and when I did that, this was in meters per second, and this was in seconds. So this is going to be meters per second, or meters per second squared. No, then it would be a non-uniform acceleration. If it was a curve, it's still accelerating, but it's not accelerating uniformly. Okay, so yeah, it would be a lot more difficult. Not that you're going to deal with, no. No, we deal with pretty linear stuff. All right, so what we've really done here, guys, is that we've found a way to calculate acceleration. And when we did that, we were taking two different speeds and dividing them by time, right? We were taking these two speeds and we were doing what with them? We went this speed minus this one. Agreed? Okay, so I took the final velocity and I subtracted the initial one. Because at time 0, this is how fast I was going. That was initially how fast I was going, 2 meters per second. At the end, I was going 8 meters per second. So that's final minus initial divided by time. Okay? That's the acceleration formula that you're going to use in this course. We're not going to deal with that till the end of the week probably, okay? But that's where it comes from. Okay? Calculating the slope of the line on this graph is where they got that formula from. Okay? And you just derived it. Okay? Don't worry, guys. We're going to spend some time working with graphs a little bit. Okay? Graphing is like the most important skill you can have in science. So graph interpretation is something we spend a fair amount of time on. Okay. All right. Okay, so on a velocity versus time graph, obviously we can read the velocity right off the graph. That's what this is saying here. The vertical value of any point is the instantaneous velocity at any time. You can read the velocity off the graph. Okay, and also the area under the line on a velocity time graph is equal to the displacement of the object. Okay, and that's what we did with this. Okay, really we're saying average velocity was total displacement over total time. Okay, that's how we got that. Okay, because the area underneath the line represents using that equation. Okay. Actually, you know what? We're going to go back and use this graph again. Okay. Just because I want to redraw it, I've already got it drawn here. What's the total displacement of this object? Just because we've done it, one like it, but this one's got an extra little trick in it. Okay. We want to find out the total displacement of this object. Okay. What did we do the last time I asked you to do that? Right, we multiplied the average velocity by the time. Okay, but that assumed that we started at, yeah, did we start at 0 here? No. Okay, so because this object's accelerating, okay, we've got basically two parts to this graph. We've got the part of the graph where it's accelerating, and we've also got, here's how far it would have gone if it stayed at 2 meters per second. Okay, you guys follow me there? So I have to take how far it would have gone if it stayed at 2 meters per second, and I've got to add that to how far it goes while it accelerates. So I can find the average velocity during this triangle part, okay, and figure out how far it goes, and then add that to this. Okay, remember that here it says it's the total area under the line on a velocity versus time graph. Okay, well, the total area here is a triangle and a rectangle. Okay, now there's other acceleration formulas that you don't deal with in Science 10 that deal with that situation. Okay, but as long as you understand that once in a while, not often, you're going to deal with that. Okay, not often though. Okay, let's look at it in an easier way. Let's look at it like this. Okay, just so we got the values. Okay, so it's a velocity versus time graph, and I want to calculate the total displacement of the object. Okay, I want to find the total displacement of the object. Here, in this first part, the object is what? It's accelerating. Okay, but can I still use average velocity, okay, equals total displacement over total time? Yep, okay, I've just got to find the average velocity, which we said is the kind of the halfway point. So I'm going to calculate the area of this triangle. Everyone okay with that? Because that's going to be the height over 2, which is the average velocity, okay, multiplied by the time. All right, so base times height over 2. So we got 5 times 2 is 10, over 2 is 5. All right, so the area of that triangle is 5 meters. That's how far it went in that part. Okay, what's it doing here? Traveling at a constant speed. Well, figuring out how far something goes while it's traveling at a constant speed is an easy calculation, agreed? Right? We just take the constant speed of 5 and multiply it by how long it traveled at that speed for, which was 2 seconds. All right, so this is, went 10 meters there. All right, what about this part? Okay, it's accelerating here, right? But I've also got a little square underneath, right? Could I make that part of this whole big rectangle here? Okay, so that's what we'll do. We'll do this triangle here, okay, whose height is 3, and its base is 1. Okay, so 3 times 1 is 3, over 2 is 1.5. Everyone follow what he did there? Okay, and then I would do this rectangle here, which has a base of 4 and a height of 2. All right, what do I do with those numbers? Add them all up. Okay, they're all positive. Okay, so the total displacement would be 18, 23, 24 and a half meters. Yeah. Right? Does it get any different if the graph does this? I would be adding and subtracting, okay? Because if it wants me to calculate the total displacement, I've got to take into account that for part of this trip I was going backwards, all right? So I still calculate the displacements or how far it went in each of these sections. It's just these ones are negative and these ones are positive, okay? In fact, for this one, because I tried to draw it symmetrical, it would be 0 because it spent just as much time above the line as it did below the line. Okay, little things like that. All right. Push the right button. Okay, so for number 1 here, guys, it's a position versus time graph, and that's the big thing. Whenever you approach a graphing question, the most important thing is to look at what kind of graph it is, because obviously the way you solve for things is different depending on the type of graph. Okay, so if we want to find the total displacement, we look at where it started, 0.2 meters, and where it ended, 0.5 meters. All right, final position minus initial position, 0.5 minus 0.2. Our total displacement then, okay, is 0.3 meters, and that would be positive because they didn't tell us forward, backward, or whatever. It's just positive. Okay, total distance traveled. Okay, we said we have to put all the sections where it actually moves together. So it goes from 0.2 to 1, so that's 0.8, and then from 1 to 0.5, so that's 0.5. So our total distance traveled is 1.5 meters. We don't put a positive or a negative on that because it's a scalar quantity. All right, average velocity, total displacement over total time. So 0.3 divided by 7 seconds, okay, and we'll have our 0.04, positive 0.04 meters per second. And then for speed, it's total distance over total time. So 1.5 over 7 seconds gives us 0.19 meters per second. Sorry, yeah, because Codair can't add. Yeah, 1.3. Okay, the answer's right there. It's one of those days. It's Monday. It's Monday. I blame Monday. Monday gets blamed for everything. All right, let's leave it at that. Okay, just leave her there. All right, that way you got enough to keep you occupied for tomorrow. Okay, when the sub is here.